Rational expressions. We're going to be using expressions that have rational exponents, meaning fractions, and we're going to switch them between an exponential form and a radical form. So the first thing that we have to recognize is that when the radicand is a positive value of b, we can have real solutions. And when it is a negative value, then that means that we're going to have that complex solution or imaginary number. Here's an example of switching from the exponential form to the radical form. What I want you to notice is the denominator in the rational becomes the index of the radical. So we go from the exponential to the radical. The numerator actually becomes the exponent on the radicand. In this case it's a 1, so we don't actually have to write it, but in other examples, such as, let's say if I said a to the 2/3, we could write that as the cubed root, so the denominator of the rational becomes the index, a squared. You can also write it like this, and it's the same thing. If I want to go from the radical form to the exponential form, remember that's the same as the square root. So my radicand is the w, my exponential would be the 1/2. Now there's a couple of different ways to do this, and so I'm going to start with one method and then show you another method. Now, first of all, that negative on the exponent means that we need to take the reciprocal. So 49 is the base, so it goes into the denominator and the exponent becomes positive. Now I'm going to change this to the radical form. So I'm going to get 1 over the square root of 49. And then I simplify that to be 1/7. So that's one way we can answer this question. The other way we can answer this question is 49 to the negative 1/2. The other way we can answer this question is by simplifying the base. And we can simplify that to be the same as 7 squared. So 49 is equivalent to 7 squared. Then we leave that negative 1/2 on the outside. And then we do the power of a power as our exponent law. So we multiply those together. And then we just simplify it with 1/7. I don't care which way you do it, I'm just showing that there's multiple ways to get to the same answer. So here's another one. We have two different methods again that we'll look at. 32 is our radicand. We're going to go to the radical form. The denominator is 5, so that's going to stay on the outside as our index. And the numerator, which is a 2, I can put right there. Or, same thing on the outside. To simplify 32, 32 is the same as 2 to the 5th. So I can cancel those, so I'm left with 2 squared, which is equal to 4. The other way to do this is to leave it in the rational form, change 32 to be 2 to the 5th, multiply these together, so we end up getting those cancel, so we get 2 squared, which is equal to 4. So we get the exact same answer. So one is just staying within the rational exponent form, the other one is changing to a radical. Here is just a breakdown of what I was speaking about earlier in terms of if the numerator has a value other than 1, it becomes the power on the radicand. So here it shows that it can be underneath the radical or, as I showed you, on the outside of the radical. Now we're going to mix in some more exponent laws. So when we have bases that are the same, that means that we can add the exponents. That's my final answer. Here, I see that there's a negative. So what I want to do is I want to get rid of the negative. So I take the reciprocal of the base, which is now 1 over x, and now it's raised to the positive 2/3. Now here's the thing. Although this doesn't look like a radical, it actually is because it's equivalent to 1 over the cubed root of x squared. And as we learned in an earlier section, we can't have a radical in the denominator. So what we're going to do is we need to multiply this by the cubed root of x. And the reason why we do that is because now our numerator is the cubed root of x and our denominator is the cubed root of x cubed, because we multiply these together, meaning that when the bases are the same, we add the exponents, so these can cancel. So I showed you the radical form because we're familiar with it from an earlier section, but you could leave it as another method in just the rational form. We could multiply this by x to the 1/3 over x to the 1/3, which is equivalent to what we did. It's just in the rational form. Then we're left with x to the 1/3 over, because x to the 1/3 times 1 stays the same. Add the exponents here, so we just get x. Now we can even simplify this further. So that is our final answer. This or this, which is the exact same. So the first thing I'm going to do, because the radicals aren't the same, I'm actually going to change this to rational form to get a different view. I want to get it to the point where I have the same bases, and I can make the base, I can make 16 to have a base of 2, because it's the same as 2 to the 4th. I can multiply the power of power and simplify it. Then I have bases that are the same, so I can subtract the exponents. So that is my final answer, or in radical form, there's my final answer. Okay, so I'm going to change this. So I changed it to a rational. Then I can multiply this through. So I get 4 to the 1/6 and x to the 2/3, because I multiply those. That gives me 4 over 6, which is the same as 2 over 3. If I want to simplify this further, I can change this to be a base of 2. And so that would give me 2 to the 1/3, x to the 2/3, which is the same as this. For the last one, this kind of incorporates simplifying the rational exponents as well as using that conjugate rule in the denominator. Remember, this is the same as square root of y plus 1 over the square root of y minus 1. That's what this question is equivalent to. And we can't have a radical in the denominator. So that means that we have to use the conjugate because it's a binomial to simplify the denominator. So plus 1. I use the exact same terms, but I change the sign from a negative to a positive. Then I'm going to FOIL. So in the numerator, I get y to the 1/4 plus y to the 1/2 is equal to y. Inner plus 1y/2 outer is plus y to the 1/2 plus 1. On the inside here, when I multiply these together, I get y. The inner and outer cancel, and then I'm left with minus 1. So I'm going to collect like terms. So y plus 2, y to the 1/2 plus 1 over y minus 1. And that's my final answer.